We'll get started again here. The reason Bohr model failed was energy only depended on n here, and also the visualization of orbits versus orbitals. Here in quantum mechanics, the energy is going to depend on n and L to a lesser extent. And so here, there are different ways of representing that. We can draw these individual lines. Here they have circles. Previously they had boxes. And so here we have one orbital. The next orbital is here. The next orbital is here, here, here. So we can see 3s orbital is going to be lower in energy than the 3p. And this is the next letter designation. When L equals 2, we have the d orbitals. When L equals 3, we have the f orbitals. When L equals 4, do you know what type of orbitals those are called? L equals 4. Just take a guess, based on the pattern. Do you see a pattern? Maybe it's hard to see the pattern here. But if you were to guess, what letter would you guess? G. G is correct. It goes alphabetical. After S and P have their origins in spectroscopy. S stands for sharp, the sharp line. P stands for the principal line, the big one. D stands for diffuse. But then it goes just alphabetical, F, G, H, etc. That's what we have here. Now, do we need to know the mathematical pattern? The only reason we need to know the mathematical pattern is if you want more predictive power. So, for example, a lot of people will just memorize this. They'll memorize it up to about 3D or 4P here. So they can memorize that without too much difficulty. But if somebody were to ask, if n equals 25 and L equals 25 and L equals 20, how many orbitals are there? What letter are they? This kind of stuff. You wouldn't be able to answer that question easily. And so to make your predictive power a lot better, we can look at, we aren't going to solve the Schrodinger equation at all. All we're going to do is we're going to do this. Based on the Schrodinger equation, we get three numbers that define orbitals. Three numbers define an orbital. N, which is called the principal quantum number. Q number, abbreviated, principal quantum number. It's very much related to energy. Can equal integers from 1 to infinity. We'll have an infinite number of n's in this diagram. So this diagram is missing most of it, but it's at the most important part. The most important part is right at the beginning. L is the angular momentum. Azimuthal quantum number. Next will be on L takes on all values. From 0, 1, 2, ... to n minus 1 for a given n. So for example, if n is equal to 2, then L will take on all values up to a max of n minus 1. And so if n equals 2, then we can have L equals 0, we can have L equals 1, but we cannot have L equals 2. Why is that? We cannot have L equals 2 because that would violate this. The maximum is n minus 1, the maximum L value. And So here, if n equals 3, then we can have L equals 0. We could have L equals 1. We could have L equals 2, but we cannot have L equals 3. The reason for this is this would violate the mathematics of the Schrodinger equation. The Schrodinger equation would fail for those values, and that would not be an answer. In other words, it would not be an orbital in a allowed state. Well, the angular momentum, this tells us the shape and energy for multi-electron. For single electron, in both quantum mechanics and the Bohr model, the energy only depends on n. Why? That's discussed heavily in Chem 1A. I don't want to get into it. Chem 4. Skip it. All right. After L, we have M, which is the magnetic quantum number. Why is it called magnetic? There's reasons, but we're not going to get into the reasons why they're called what they're called. We're just going to learn the mathematical restriction. And so M will take on all values from minus L to minus L plus 1, dot, 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 through 0, dot, 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 to L plus L minus 1 to L for a given L. And so we can label these. It turns out there are 3 orbitals. There are 3 2b orbitals. The reason there are 3 2b orbitals is because L is 1. If L is 1, we have 3 m values. The m values would be minus 1, 0, and plus 1. That goes for all these. All these have minus 1, 0, plus 1. If L is equal to 0, then all we're allowed is 0. We go from minus 0 to plus 0. So 0. So there's only one orbital. If L equals 2, how many are we allowed? Well, if L equals 2, then we go from minus 2 to plus 2. Minus 2, minus 1, 0, plus 1, plus 2. So that means there are 5 what we call d orbitals. 5 d orbitals. If L equals 3, then we're going to go from minus 3 to plus 3. Minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. And that means there are a total of 7 orbitals. If L equals 4, how many orbitals are there? 9. If L equals 10, how many orbitals are there? 21. And so there's a very simple mathematical pattern for this. For each L, L is also called a sublevel. You know, if this is our principal energy, then this is our sub-energy or sub-level for energy. So this is called a sub-level. And so for each L that is sub-level, there are 2L plus 1 orbitals. All right, with these simple mathematical equations, we can figure out all infinite number of orbitals if we want for the hydrogen atom. Well, situation is the hydrogen atom, you know, where do you think that electron's most comfortable being? On the top floor or the ground floor? Yeah, nature wants to minimize energy. And so if we have a if we have an H atom, you know, the electron can be in any floor it wants, you know, including sublevels here. Right? It can be on any floor it wants. However, the lowest energy would be down here. And so for the hydrogen atom, the lowest energy is if the electron is on the first level, or first energy level, or principal energy level. And this would be called the ground state. Ground state. Now, an excited state means the electron gets promoted to a higher level, any of the higher levels. These would be excited states. The electron gets promoted higher. If the electron gets promoted to n equals infinity, then we call it an ionized electron. We call this ionization. That is, if we take the electron and promote it from the ground state all the way up to the n equals infinity state, well, infinitely far away, which means the electron has been completely dissociated from the atom. Well, how far away is infinity? It's not far, actually. It's just above this. In terms of energy, it's not far. And so let's see if we can see other. There are a whole bunch of different ways. This is the same thing. This is the same kind of representation, but you see this has more levels that they're going up. And then they're plotting this, the energies. You see how the energies start to compress as we get higher and higher? And they're more spread out down lower. This is not a good one. This is like your book. What don't I like about this? What I like about this is there's a 1s, 2s, 2p, but what I don't like is how many 2p orbitals are there? There are 3, and they're indicating the 3 by drawing a longer line. Do you see this line is 3 times longer than this one? And this line is going to be 5 times longer than this one. But how do you know? How many times longer is that one? You want to just eyeball that? And when you get to higher and higher ones, you want to measure it? This is ridiculous. And so this one I don't like at all. Let's see some other good ones. This is good. This is easy to see. Each orbital is a circle. It's easy to see. I like that. How about this one? Do you like this one? Oh wow, this you know what this one's from? This one's from the Chem 1A book. There's more to it, which we aren't going to get into. There's reasons why this 1s is higher than this one. We don't really care. We're just looking at the pattern right now. This is for the hydrogen atom. Remember that for the hydrogen atom, the energy only depends on n. This is why Bohr thought he had it right. But it failed when he went to multi-electron, because in multi-electron, the energy depends on n and L. So multi-electron, single electron, hydrogen atom. So these are good. Where they represent the orbitals with lines here, which is fine. Let's look at some more to get a good feeling of the variation in representing these. This is something else. This is for molecules. Much surge. How's this one? This one looks pretty good because here I have my 1s, which is the 100, and then here I have my 200, or the 2s, and then I have my two 1 orbitals, or the 2p orbitals. 2 1 negative 1, 2 1 0, 2 1 1, and then it goes up to 3s. Why don't I have a 1p orbital? Am I missing a 1p orbital? I don't have a 1p orbital because that would violate the Schrodinger equation. Because the maximum L is n minus 1. And so if n is equal to 1, a p orbital is not possible because that would mean L would have to be equal to 1, which would violate the Schrodinger equation, which means it's forbidden. So all these other states are forbidden. But this is allowed. Here I have 3d, but where's my 2d? Don't I have 2d orbitals? No, because that would violate Schrodinger equation. And so we could figure this out like this. But you can see now the 3s, the 3p, the 3d would be the highest in energy. But do you know these orbitals start to contract in a way? They start to converge. And it's tricky. Do you see? Look at the 4s and the 3d. 4s should be higher in energy, but the 3d gets kicked up because of its shape. You know, look at the p. Do you see the s orbitals are spherical? The p orbitals are this dumbbell shape. The d orbitals are cloverleaf shape. Actually, there are two different shapes of the d. One is a cloverleaf, so this is one orbital here. Another is this. It has this hula hoop here. It's like a p orbital with a hula hoop. This is another one. This one we call the dz squared. These would be the others. So we have 5 of those. But you know, something's going on with the energies here. You know, shouldn't the 4s be higher, but it looks like it's lower. And so there's one more thing you have to remember, and that's the relative energy. There's a pattern with the relative energy. The pattern with the relative energy goes like this. Of course, we can calculate it using quantum mechanics, but we aren't going to do any math. And so we're going to try to do this without math, which means we're going to try to come up with as many patterns as possible. And so one of the patterns is this table, like this. We add one extra column here because of quantum numbers. So we got 4s, 4p, 4d, 4f, and then 5s, 5p, 5d, 5f, and then what comes next after 5f? 5g. What about 5h? Is there 5h? There's no 5h. That's forbidden. Is there a 6h? Is 6h possible? Yes. There is a 6h, but there's no 5h. And so the pattern goes like this. This doesn't always work, but it's easy to remember. And so the energy order goes 1s to 2s, from 2s to 2p, 2p to 3s, 3s to 3p. Here's where it gets tricky. 3p goes to 4s, not 3d. So we go 3p, 4s to 3d, to 4p to 5s. And so this is how the energies are ordered here. 1s to 2s, 2s to 2p, 2p to 3s, 3s to 3p. 3p doesn't go to 3d, 3p goes to 4s, or 4s goes to 3d. Now they're all mixed up. If the orbitals are all mixed up, now how do we keep track of them? There are two ways we keep track of them. We keep track of them by the n energy level. And so this is a bit weird. The n equals 3 energy level consists of 3 sets of orbitals. Each of these are called subshells or sublevels. We have the 3s subshell, the 3p subshell, the 3d. So the n equals 3 has these. But we have another word called shells. And the shells are a group of orbitals that have similar energies. And so this 1s stands all by itself. So this consists of one whole shell, but it only has one orbital in that shell. The next shell of orbitals will be the 2s and the 2p. The 2s and 2p are very close in energy, so we'll call this the second shell here. Now the third shell is a bit tricky here because the third shell is going to just consist of the 3s and the 3p because the 3d are way up there in the, so we're going to put the 3d in the fourth shell. And so the 3s and the 3p are the third shell here. And then the fourth shell is going to consist of the 4s, 3p, and the 4p. So, but where's the 4f? The 4f are in the fifth shell. And so it's a little bit tricky, this whole idea of shells. We don't have a simple thing for shells. That's good. Okay, let's look at some other diagrams here. This is an orbital diagram, but it's written horizontally like this. when you don't have enough space, you can write it like this, but you lose information. So we don't like to write it like this. We like to have more information show up. Oh, look at this one here. This one's looking pretty good. Except I don't like this necessarily, this notation. Because n equals 3, when n is equal to 3, we have the 3s, the 3p, and the 3d. But what they're talking about are shells here. In the third shell, we only have the 3s and the 3p. The other n equals 3 orbitals out. And so I'd probably call this a shell. First shell, second shell, third shell. We call n equals 3 the energy level, so that would be this. Although, it gets kind of mixed up. So here again, this extends out. So in the fourth shell, we'll have the 4s, 3d, 4p. In the fifth shell, this is what we're going to have. We're going to have 5s. It's going to go 5s over there. What's after 5s? Look at that chart over there. After 5s comes 4d. After 4d comes 5p. And so on. And so we can get the shells this way. The easiest way to get the shells, you'll see in a minute, there's an even easier way to figure out what the shells are. So this is another one. What do we call these diagrams? Do you know what these diagrams are called? These are, here's another way of representing this. I don't like this one because it just shows the gaps in energies the same. So the same gap in energy between 1s and 2s. So the 2s and 2p have the same gap in energy. This is not accurate enough. I don't like that diagram at all. It's nice because of the colors, but other than that, forget it. Same thing with this diagram. This diagram is 4 too. Because of the relative energies. Do you see that? I'll talk about what's going on with the arrows in a minute. This is a good diagram. We'll talk about this. This is getting into the full quantum mechanics. This is a poor diagram. I like this diagram. Well, maybe not. This diagram is not so good because it's hard to see the shells. Same thing with this one, this diagram, it's hard to see the shells. Hard to see the shells. Easier, but this is only for hydrogen. Do you see for hydrogen? Energy only depends on N. Those are for molecules here. I need to refine my search. I didn't do it good enough. I need to call this atomic orbital energy level diagram. Ah, shit. See if I can find a good one here. Well, this one is okay. We'll just look at this one, but I would modify it just a little bit. And I just make it so that it's easier to see the shells. And so what we need to do is we need to be able to draw this diagram on paper. And so let's get some practice drawing a diagram like this. draw a diagram and label it. So we have the 1s or the 1, 0, 0. I'm going to call it NLM like this. It's 1, 0, 0. And then we have the 2s, the 2, 0, 0 orbital. And then we have the 3 2p's. We'll call these the 2p, the 2, 1, 1, 2, 1, 0, 2, 1, minus 1. Put those in parentheses, keep those separate. Some people call this the px, py, pz. Then we have the 3s. After 3s comes the 3p. 3p like this. So this is 3, 0, 0, 3, 1, 1, 3, 1, 0, 3, 1, minus 1. It doesn't matter the order. You can do it in any order you want. Okay, so this is the first shell. First shell. The second shell takes us up to the 2p. This will be the second shell. The third shell only goes to the 3p. The third shell. Now the fourth shell is going to include these orbitals. It's going to have the 4s, 4, 0, 0 orbital. Okay, after the 4, 0, 0, then it's going to have the what? After the 4, 0, 0, the 4s, it's going to have the 3d. So I'm going to write the 3d orbitals over here. This is a different L. So this would be 3, 2, 2, 3, 2, 1, 3, 2, 0, 3, 2, negative 1, 3, 2, negative 2. So I have my 5d orbitals, 5 3d orbitals here. And then it would go to 4p. And so I'm going to have my 4, 1, 1, 4, 1, 0, 4, 1, negative 1. These are my 4p orbitals here. And this is the fourth shell. Actually, I should do this in a different color here. Yep, all these lines are going to get mixed up. So the first shell goes here, second shell goes here, third shell goes here, and the fourth shell goes here. And so we should know this to the fourth shell. That would be the best. Fourth shell. Of course, we could go to higher and higher shells if we wanted to, but we aren't. All right, so this is kind of our map, of where the electron can be in the atom, as far as energy and position. The position is given by the cloud, the shape, the position. The energies are given by this here. And we have a cloud like that because of the Heisenberg uncertainty principle. Okay, the next step is we need to put electrons in there. So the electrons can go in any of these because these are all allowed. But what we want to do is we want to get the ground state. The ground state, what that means is we want the lowest possible energy for all the electrons. And so if I have 2 electrons, I'm going to put the electrons in the lowest possible energy orbital if I can. And so there's one more thing. And there's some guy named Pauli. And we have something called the Pauli exclusion principle. There's a fourth quantum number. The fourth quantum number is called F. So, how about that? The first 3 quantum numbers define the orbital, where the electron is in terms of position and energy. The fourth quantum number defines something, this is purely quantum mechanical, when an electron has a spin associated with it. A spin is like a magnetic moment. It's like a little magnet, north pole and south pole. And so this would be spin up. An electron can either be spin up or spin down. And so from the math of quantum mechanics, we get S. S is equal to plus 1/2 or minus 1/2. This is the fourth quantum number, which is spin. Now, The Pauli exclusion principle says this: no two electrons in the same atom, no two electrons in the same atom can have the same set of 4 quantum numbers, can have the same set of 4 quantum numbers. And so the conclusion here is that each orbital can hold a max of 2 electrons. Each orbital can hold a max of 2 electrons. Spins must be opposed. Must be opposed. So how many electrons does hydrogen have? Hydrogen has 1 electron. So if we look at hydrogen, this is the 1s with 1,0,0 orbital. Hydrogen can have 1 electron spin up, or it could be spin down. If it's spin up, then what we call this electron is 1,0,0, which positions it, plus 1/2, which tells me it's spin up. And so this is NLMS. N is equal to 1, L0, M0, S is equal to plus 1/2. This one has got to be different. This is going to be 1,0,0 minus 1/2. And since there are only 2 spin orientations, we can't put a third one in there, because the third one would either have to be plus or minus 1/2. And that would be a violation of the Pauli exclusion principle, which means it doesn't work successfully. And so it doesn't matter if it's spin up or spin down, unless you put it into a magnet. If you put it into a magnet, then of course it's going to make a difference if it's aligned with the field or opposing the field. But in space, it doesn't matter. And so here, just out of convenience, I'm going to put the first electron spin up like this. Hydrogen has 1 electron. This is what we call the ground state. The electron is in the lowest energy possible. It can be excited to higher energies, no problem. Helium has how many electrons? Well, this electron's called 1,0,0 plus 1/2. Helium has 2 electrons. And so the second electron must go in the 1s orbital. And so this would be 1,0,0 plus 1/2 and 1,0,0 minus 1/2. What if I threw in, just out of curiosity, what would this electron be called? If there's an electron here, what would it be called? See, let's say it got excited. Boom, got excited up here. We call this electron a 3,1,0 plus 1/2 electron. And so this way we can position the electrons uniquely, because each one's going to have a unique set of 4 quantum numbers, so we know exactly where it is. If we say, I'm looking at a 4,0,0 minus 1/2. Tell me where the electron goes. In the 4s, spin up or spin down? Spin down. Yeah. And so this is hydrogen. Hydrogen has filled its first shell. Now the periodic table, the way the periodic table is arranged, it's arranged by shells. And so let's take a look at the periodic table in terms of shells. This is weird alignment, but whatever. We'll just go with it. So hydrogen has 1 electron, right? It's in the 1s orbital. In the helium, there's 2 electrons. Both electrons are in the 1s orbital. And so that fills up the first shell. And so this first row has filled up the first shell. Let's take a look at the next element. After helium comes lithium. Lithium has 3 electrons, so the third electron is going to go here in the 2s orbital, right? And then we have beryllium. Beryllium has 4 electrons. It's going to fill the 2s orbital. So the first electron goes in the 2s, the second electron fills it. Once we fill up the 2s orbital, then carbon has, or boron has 5 electrons. So the 5th electron is going to go into any one of these. It doesn't matter which one because they're all the same energy. And it doesn't matter if it's spin up or spin down. And so boron is going to look like this. Just out of convenience, okay, so this is lithium, beryllium, and then boron, just out of convenience, we'll just put it in the first one and spin up. It doesn't matter. And so this would be boron. Carbon would be where? Carbon would have another electron. Now we have another question. Should we pair or should we put it in a different orbital? It turns out that we want to put it into a different orbital. And this has to do with Hund's rule. So we talked about the Pauli exclusion principle. Let's talk about Hund's rule next. Hund's rule states that we fill degenerate orbitals one at a time. Fill degenerate. Degenerate means the same energy. Energetically degenerate orbitals one at a time with parallel, not anti-parallel, with parallel spin. And so what that means is that the next electron, we aren't going to pair it here. The next electron will either occupy one of these two. It doesn't matter which one because both are 90 degrees. And so we'll just pick this one. And it's going to be parallel spin. So if the first one goes in spin up, the second one's got to go spin up. And so this would be carbon. Carbon would have 2 electrons. And then nitrogen, this would be nitrogen. So nitrogen, we've half filled the P. And so this is what we call the P block. And so nitrogen has half filled it. And then we have oxygen. Okay, now oxygen, we have to pair. And it doesn't matter which one we pair, but when we pair, it has to be opposing spin, otherwise we'll violate Pauli. And so this would be oxygen, fluorine, and then finally neon. So neon has completely filled the second shell. Now that's what gives it some special property. Helium is very unreactive chemically. Neon's very unreactive. We call those inert or noble gases. And so these filled shells are stable, unreactive. Partially filled shells are more reactive. They either want to fill up or they want to lose their electrons. And so an example of one that wants to lose rather than fill up would be sodium. Sodium has 1 electron here. So for sodium, it's just easier to lose one than to gain how many? It'd have to gain way too many to fill up that shell, right? And so if it loses it, then we're left with what we call the neon shell. And so the sodium, etc. So you can see based on the periodic table, here we're going to fill the 3rd shell. The 3rd shell consists of the 3s and the 3p. Okay, after we fill up the 3rd shell, then we're going to fill up the 4th shell. When we fill up the 4th shell, what does the 4th shell consist of? The 4th shell consists of the 4s, the 3d, and then the 4p, and so on. So that's what we're going to be doing next time. I think we'll be filling up these shells. This time I have your exam. I'm going to give it back. I didn't total up the points though, so you can total up the points. I'm going to total up the points including the multiple choice and put that on Piazza. So I'm not going to separate the score thing. I'll just put it all together.